Okay, today we're going to be talking about the post lab for a cart rolling down the ramp. In this screencast, I'll be talking about qualitative observations from the lab, velocity versus time graphs for things speeding up, how our motion maps will change for this unit, and curved position versus time graphs and tangent lines. So one observation that we were able to make from the lab is that we know that when we release the cart from rest, so it began with a velocity of 0 meters per second, we saw that it sped up because it starts at rest at 0 seconds, let's say, and then it begins rolling. A second later, it will have some type of velocity, and I'm just doing a rough motion map. This isn't really an official one. Maybe another second later, at 2 seconds, it rolls faster. 3 seconds, it rolls faster than that. And then at 4 seconds, it rolls even faster than that. Notice that each second, the cart covers more distance because it's just going faster and faster. So we know two things already. The first thing is that the cart moves in a positive direction, and it's also speeding up. And what we're going to be talking about in the screencast is just talking about how we show this in our different representations with position time graphs, velocity time graphs, and motion maps. Alright, so I believe that the easiest way to think about something speeding up is to first look at a general velocity versus time graph where something's velocity is increasing and it's moving in the positive direction. Now here, we know that it's moving in the positive direction because our graph takes place in the positive region of the axis. Okay, it's above the time axis, and we also know that it is speeding up because its velocity increases. So it increases that way. Now what we want to do is come up with an equation, a general equation for this graph. So here, we'll take note that similar to our old position versus time graphs in the old unit 2, we've got the y-intercept for our velocity time graph. This is what we'll call v sub 0, or the initial velocity. Okay, now it's called the initial velocity because it's whatever the velocity is at the beginning of the time. So in the lab, it'll be 0. Just in this general case, it's a non-zero number. Now we also have the slope, which is our m. But here in this unit, it is called acceleration. And its symbol is a. And in the same way that slope is the change in y over the change in x, here, since our y's velocity is the change in velocity over the change in time. Okay, so that's one equation that we have. It's an equation for acceleration. So we've got acceleration is equal to the change in velocity over the change in time. Now I will put this up on our board in front of the room, but we have this equation that defines acceleration. Using our y equals mx plus b, we can come up with a general equation, y equals mx plus b. We can write that for this graph, our y is just velocity, our m is acceleration, our x is time, and our y-intercept is the initial velocity. And there we go, we have our first equation from this unit, which is the constant acceleration equation. So that's the initial velocity, and this is acceleration. So I want to give you two definitions of acceleration. First up, the graphical definition is the slope of a velocity versus time graph, like I said before. And just like any slope, it's a rate of change. And in this case, it's the rate of change of an object's velocity over time. This is measured in two ways. They both mean the same thing. It's measured in meters per second per second. So here it's really meters per second over seconds. Or you'll most often see me write this, and in the worksheets, meters over seconds squared. So these two things are really the same thing. But in the beginning, I do like to use this way a lot because it just, I think it helps us understand what acceleration really is. Okay, so here's just a quick example of what this means. So what does it mean for an object to accelerate at positive 2 meters per second per second? Okay, well, what that means in a for every statement is for every 1 second, the object's velocity changes by positive 2 meters per second. So, in other words, every second that goes by, we're going to add 2 meters per second to its velocity. So in this case, and I'm just making up an initial velocity, let's say the object's velocity starts here at 0. What's going to happen is that a second later, we're going to add 2. And another second later, we're going to add 2 to that. Okay, so at 2 seconds, it will have 4 meters per second. At 3 seconds, we're going to add another 2 to that. And at 4 seconds, we're going to add another 2 to that. So as you can see, when I connect these dots, look at the velocity versus time graph that we obtain. It's a graph that's in the positive region. It's above the time axis, right? Right, this is 0. And we've also got something that's increasing in numbers. So we've got an object that started at 0 and ends with a velocity of 8 meters per second here. So clearly we see that it's speeding up and it's moving in the positive direction. Again, the positive comes from the fact that these are all positive numbers here, and all the negatives are down here. Okay, so now that we've talked about velocity versus time graphs, I think it's worth it to talk about how this might change our motion map. So first off, we've got this motion map that we kind of started our screencast with, but all I'm doing is I'm making it flat, okay? But still, we see that it's speeding up. Every second, the velocity arrows will get longer, okay? And notice that at the beginning, it starts off with no arrow because it starts at rest, and then later on we've got some very long arrow because it has sped up. One thing we are going to add is a way to show acceleration. We have to add acceleration half arrows. So what I like to show here is every dot will get a half arrow, and they look like this. Okay, notice that it doesn't have the bottom part of its head. It just kind of looks like a check mark that's fallen over. So each dot will get this. And I'm still working with this example of positive 2 meters per second per second. Okay, so it's still accelerating. We're still working with our previous example. So here, this dot will get plus 2 meters per second squared. So will this dot, the 1 second dot, gets a plus 2 meters per second squared. This dot will also get one. Plus 2 meters per second squared. And this one here also gets one. Plus 2 meters per second squared. Now notice that all of these accelerations are the same. In this class, we will only do constant accelerations. Okay, so what does this mean in terms of our velocities? Well, initially, we start off with 0 meters per second. Notice that 0 meters per second because there's no dot. And then a second later, based on what we know about our acceleration, we should have 2 meters per second. 2 meters per second. Okay? And then another second later, we should have 4 meters per second. And a second after that, we should have 6 meters per second. And then a second after that, we will have 8 meters per second. So what this means is acceleration is really adding to the velocities. And the way I think about this is that the acceleration adds to the current velocity to give us the next one. So notice here, if you follow my mark here, we've got plus 2 adding to 0 gives us 2 meters per second a second later. Adding 2 again gives us 4. Adding 2 again gives us 6. Adding 2 again gives us 8. And you can tell the next one, adding 2 again, will give us 10 somewhere along here. Okay, so acceleration, when acceleration is in the same direction as velocity, we have something that speeds up. And again, we see something moving in the positive direction and speeds up, except this time we're talking about a motion map. Okay, so finally for the screencast, what we're going to look at now is how our position versus time graphs change. Now, one of the most striking things that you'll see is that we now have curved graphs for our position versus time graphs. These are exponential or quadratic. Some phrases you may have heard in math. All that means is that it's curved. So our position versus time graphs no longer have to be straight. Okay? And right now, based on what you knew last unit, all we can really conclude now is that the cart moves in the positive direction. How can we tell that? Well, we know that it starts here at 0 and it ends up at 8, so its position just increased. Okay, so the fact that it just increased means that it's moving in the positive direction. All right, so this is the shape of the graph that we got from the lab, and we want to figure out how we can tell it speeds up. So what I'm going to do is I'm just going to take two places in time. I'm going to take 2 seconds and 7 seconds. Okay, these are just random ones that I chose, and we're going to draw a tangent line at both places. So I'm going to cut through the graph at 2 and draw this blue tangent line where 2 seconds happens, and I'm also going to draw another tangent line in blue where 7 seconds happens. Okay, and I want you to take note of what those lines look like in comparison to one another. And here we're going to introduce this idea, a new definition for us, instantaneous velocity. So here in this unit, since we're talking about things that are accelerating, that means that an object's velocity is changing, can either increase or decrease. We have to have this new word specifying that we have to be specific about velocity now. So here we've got the word definition of instantaneous velocity. It's an object's velocity at a specific time. And in terms of a graph, this one's kind of wordier. It's the slope of a position versus time graph's tangent line at a specific time. So here, what we're going to take a look at is we're just going to compare how the steepnesses compare for the 2 second tangent line and the 7 second tangent line. And you'll notice that for the 2 seconds tangent line, we've got something that's very shallow. And that means it's slower, right? This is not new to us. We knew this last unit. And here we've got something that's steep. And therefore, that means it's moving faster. Okay? So by definition of what it means to speed up, we know that it's moving slow first and then moves faster. Therefore, it's speeding up. Okay, so this is just a qualitative look. No numbers yet, except for the 2 seconds and the 7 seconds, but just taking a look at how we can tell something's speeding up. Okay? So again, here we have another representation, a position versus time graph that tells the same story as a velocity time graph that we looked at before in the motion map, that we looked at a few slides ago. So we've got something that moves in a positive direction and speeds up. Alright, so it turns out that there's actually much more to this unit than that. We've only really covered a quarter of these representations that we're talking about because this is only moving forward and speeding up. We still have to take a look at what the shapes of our graphs and our motion maps will look like for the other three. Something moving forward and slowing down. That's another thing. Something moving backwards and speeding up. And something moving backwards and slowing down. So we still are not sure what those look like, but we will understand soon after a few homework assignments. Okay, so we'll talk in class.